We need to test the convergence of the series whose nth term is this. Here I am interested to use the comparison test. Why comparison test? Because for the comparison test we need two positive series. We can take one series to be square root n divided by n square plus 1 as it is, and another series to be square root n divided by n square. Now what is the comparison test? For the positive series, if limit n tends to infinity on their ratio is equal to L, the limit, which should be non-zero and finite, then both the series either convergent or divergent. Let's check this. So let me consider un to be equal to square root n divided by n square plus 1 and vn to be equal to square root n divided by n square. When taking their ratio and applying the limit, we get this to be limit on square root n divided by n square plus 1 into square root n divided by n square. Cancelling this, again if I take n square common from the denominator, these two cancel out, and when taking limit n tends to infinity I get 1. This limit is non-zero and finite. So let's take one of this series and we need to check which of the series will be convergent or divergent. The easier ways to check is from Vn. Now Vn is equal to square root n divided by n square, n power 1 by 2, n square, that is n power minus 3 by 2, or 1 divided by n power 3 by 2. By p-test, if p is greater than 1, then the series is convergent. So here I am having 3 by 2, which is strictly greater than 1. So this Vn series is convergent. So by p-test, the series Vn is convergent. And because Vn is convergent, we say that Un is also convergent by comparison test. Because for the comparison test, both will converge or diverge together. So if Vn is converging, that means Un is also converging. So by comparison test, this given nth term is convergent. So hence the series summation square root n divided by n square plus 1 is convergent. Sorry friends. Next is we need to test the convergence of this series. Now here if you look at the denominator, it is 3, 5, 7, that is the AP series. So nth term would be, for the AP series it is first term plus n minus 1 into the difference of the consecutive numbers, that is 2. So this is 2n plus 1. For the numerator, it is just the product of the numbers, the product of n numbers. So nth term would be n. For n equal to 1, we get in the numerator 1. And for n equal to 1 here, we get the nth term, the first number to be 3. Similarly, for n equal to 2, we get 2 over here, and for n equal to 2 in the denominator, we get 5. Likewise, the other numbers, right? Okay, so for this, we are interested in, because we know the nth term of the numerator and denominator, we are going to prefer the ratios test. We first take the un to be the nth term of this series. So taking its nth term to be 1, 2, 3, 4 up to n divided by 3, 5, 7, 9 up to 2n plus 1 to be the nth term, and I'm taking that to be un. And then we need to get un plus 1. And when un divided by un plus 1, when applying the limit on this, if that limit is greater than 1, then the given series is convergent. If L is less than 1, then that is divergent. And if L equal to 1, then the test fails. Right? So let's use the ratio test for this. To apply the ratio test, I'm taking un to be the product of these numbers up to n divided by the product of the numbers in the denominator. And then taking un plus 1, the product of the numbers up to n plus 1. Just replace n with n plus 1. And in the denominator we get 2 into n plus 1 plus 1. That is 2n plus 3. What is the previous term of this? It is n. And the previous term of this is 2n plus 1. So let's take these together. Now let's take the limit on un divided by un plus 1. Un is n divided by 2n plus 1 into un plus 1 is this complete ratio. So cancelling this and this, we get 2n plus 3 divided by n plus 1. Let's take n common. And also from the denominator. Now applying the limit. When n tends to infinity, we get 3 by infinity to be 0. And 1 plus 0, that is 2. Now this 2, this limit, strictly greater than 1. When the limit is strictly greater than 1, we get the series to be the convergent series. For L to be strictly less than 1, we get the divergent series. Right? 2 is strictly greater than 1, so our given series is a convergent series. So therefore, by ratios test, the given series is convergent. It is convergent. Okay, thank you.